Hi, this is Tzvi Rosen. Welcome to another lecture in our series on the history of calculus. Today's lecture will focus on Ibn al-Haytham. We'll start with a bit of the political backdrop. We're setting ourselves in the Islamic Golden Age. This was between the 8th and 13th century CE. And what's often described as the beginning of the Islamic Golden Age was the Abbasid Caliph al-Mamun in between 813 and 833 CE. He founded an institute called the House of Wisdom in Baghdad. And this was devoted to translating works of science from Greek and from Indian languages to Arabic. And this institution lasted for about 200 years. But it set a trend for state-sponsored science throughout the Abbasid Empire and other Islamic dynasties, leading to advances in astronomy, medicine, and mathematics. Some examples of mathematics in the Islamic Golden Age, we can start with al-Khwarizmi. He wrote the first text on algebra, and the word algebra actually comes from the title of his book, Al-Jabr, and that book was devoted to solving linear and quadratic polynomials. Additionally, his name is the origin of the common word algorithm. Algorithm comes from al-Khwarizmi. Sounds a little bit like algorithm. Another great Islamic mathematician was Omar Khayyam, who wrote a follow-up to al-Khwarizmi's work, solving some cubic equations. And finally, the mathematician we'll be focusing on today is Ibn al-Haytham, and he contributed to geometry, particularly the study of optics, how light travels, and number theory, as well as discovering summation formulas, and we're going to look at those summation formulas in this lecture. And he lived from approximately 965 to 1040 CE. One problem that Ibn al-Haytham worked on was a certain surface or volume of revolution. So suppose we have this curve, which is x equals y squared. Okay, so we're starting from 0, 0, and taking the curve up to 1, 1. And suppose we rotate it around the line x equals 1. The question that Ibn al-Haytham worked on was, what is the volume of the resulting solid of revolution? Okay. So the way that in modern calculus we would approach this problem is using the disk method, which you often study in Calculus 2, second semester calculus course. The idea is to compute the volume of each cylindrical slice as depicted in this image, and then integrate over all of these slices. Okay, so first let's recall that the volume of a cylinder is pi r squared, cross-sectional area, times h, the height of the cylinder. For us, r is this distance, meaning, so if we take a general slice, so we have the distance from x equals 1 to the curve x equals y squared, and the radius will be the difference, so r equals 1 minus y squared. Okay, as for the height, we're talking about an infinitesimal height of dy. Okay, so our integration is the integral from 0 to 1 of pi times 1 minus y squared squared times dy. Okay. Now, pulling out the pi, And expanding, we get 1 minus 2y squared plus y to the fourth dy. And applying the power rule, we get pi times y minus 2/3 y cubed plus 1/5 y to the fifth, evaluated from 0 to 1. Okay, at 0, all of these terms are 0, so we could just pay attention to 1, and we get pi times 1 minus 2/3 plus 1/5. Okay, and putting everything over a common denominator, we have 15/15 minus 10/15, that leaves 5/15, plus 3/15, which gives 8/15 times pi. Okay, and that is the solution to this volume problem. Okay, pretty straightforward exercise for somebody who's taken a calculus class, which is built on the advancements of millennia. Ibn al-Haytham did not have a calculus textbook with the disk method spelled out, so he had to invent his own approach. And he was certainly influenced by Archimedes' computation of volumes. And what he ended up doing looks a lot like the disk method. But what he does, instead of using the dy, because again, he didn't have the calculus, so he couldn't just integrate stuff. So instead, he had an approximation by a discrete collection of disks. So he says, let's say there are n cylinders. Then the height of each cylinder is going to be the height of each cylinder is going to be 1 over n. Okay? As for the radius, okay, so if you're at, let's say you're going up k steps, so let's say at step k over n, the radius will be equal to, well, y is k over n, so we know it's going to be 1 minus the y value squared. Okay? And so what he was doing, instead of an integral, he was doing a finite sum. And his finite sum was taking k, going from 0 to n minus 1 of pi 1 minus k over n squared, again, because you have to square the radius, times the height, which is 1 over n. Okay, and we're not integrating, we're just summing. Okay, so let's try and simplify this as much as possible. So we can pull out the pi, and we can pull out the n, and we're just summing from k equals 0 to n minus 1, 1 minus 2k, let's put this together, 2k squared over n squared plus k to the fourth over n to the fourth. Okay, so this is our summation. Okay. Now we'll split up this sum. So first we have the sum from k equals 0 to n minus 1 of 1. Okay, minus the sum, and we can pull out this 2 over n squared. Sum from k equals 0 to n minus 1 of k squared. Okay, pretty simple formula. Plus, okay, and here we can pull out the factor of 1 over n to the fourth times the sum of k to the fourth. let's just add in the bounds here of k equals 0 to n minus 1. Okay, so this sum is going to be easy to do. It's just 1 added to itself a bunch of times. But this sum and this sum, with the benefit of modern mathematics, we know how to do it. But at the time, this was as yet unknown. And Ibn al-Haytham was able to calculate a formula for these summations and was able to use that to finish his volume computation. And eventually he arrived at the same result that we did, which is 8/15 pi. Okay, but let's go into his proof of what these summations were. Okay, and for these proofs, he needs a certain lemma, which is an equation that he proved by way of induction. Whenever there's a proof by induction, there's always a question of how do you come up with the equation before you prove it by induction. And I wasn't able to find exactly how he arrived at this equation. We're going to take the equation for granted and try to prove some of these summation formulas. So starting with k equals 0, we get n plus 1 times the sum of I to the 0, I equals 1 to n, equals sum from I equals 1 to n, I to the 1, plus the sum from p equals 1 to n of the sum from I equals 1 to p of I to the 0. Okay, so I to the 0 is just 1. So we have n plus 1 times the sum of 1 n times, that's going to be n, is equal to the sum of I equals 1 to n of I plus, now we're going to simplify this first term first, or the inside sum first, to obtain, the I to the 0 is just 1, so we have p times 1, so that means we're just summing p from 1 to n. But that's just the same as the first summation, so we really just have twice that first summation. And at this point, we can just solve for the value of the summation by dividing by 2. We have the sum from I equals 1 to n of I is equal to n times n plus 1 over 2. Cool. Hopefully that's a familiar formula. We'll take it one more step further, and then hopefully you'll trust me that you could do the same for the third and fourth powers. But let's do this for k equals 1. Let's start by plugging in k equals 1. So we have n plus 1 times the sum I equals 1 to n of I equals sum from I equals 1 to n of I squared plus the sum from p equals 1 to n of the sum of I equals 1 to p I to the 1, or just I. Okay, now I'm going to expand this last term. Okay, so we leave the I squared untouched, and I'm going to start dropping indices to save time. And we have the sum of from p equals 1 to n, and we know this formula, the sum from I equals 1 to p of I is going to be p times p plus 1 over 2. That's what we derived on the last page, the last slide. So simplifying further, okay, we have the I squared. This can be split up into two terms, right? It can be p squared over 2 plus p over 2. So we essentially get 1/2 times the sum of p squared plus 1/2 times the sum of p. Okay? But the index at this point doesn't matter, so we can replace this p with I. I squared plus 1/2 I. 1/2 the sum of I. Okay, and at this point we have n plus 1 times the sum of I is equal to sum of I squared plus half sum of I squared plus half sum of I. So let's move this half over to the other side, this half sum I to the other side. So we get n plus 1/2 times the sum of I equals 3/2 times the sum of I squared. Okay? And we'll multiply both sides by 2/3 to get that the sum of I squared is equal to 2/3 n plus 1/2 times the sum of I, and at this point I'll plug in the formula for that as well, which is n times n plus 1 over 2. Okay, just giving myself a bit more space. So here we have some cancellation, the 2's cancel. Okay, and instead of n plus 1/2, we're going to turn this into 2n plus 1 over 2. Okay, and multiplying everything together, we get a solution of n plus 1, 2n plus 1 divided by 6. Okay, and that might be a familiar formula as well. And using the same techniques, you can also get the sum of cubes and the sum of fourth powers. And now, having the sum of squares and sum of fourth powers, Ibn al-Haytham was able to compute his integral. That's where we'll leave it with the mathematics of Ibn al-Haytham. This is just one example of the computations he did, but he really made a ton of contributions in various areas, and I recommend looking out for translations of his work. But I'd like to look now at a different way of getting at the results that we looked at today, and that's through the discrete calculus. This is a discrete analog of the standard continuous calculus that you studied in your first calculus courses. And it was kind of implicit in a lot of the early work in calculus, but it didn't begin being studied in its own right until the 20th century. And the idea is to work with integer valued functions on the integers. And we're going to define a discrete derivative by taking delta of f instead of df dx. Delta of f is f of n plus 1 minus f of n. It's kind of like the difference quotient from standard calculus, but fixing h, instead of letting h approach 0, you just let h equals 1. And we also define the discrete integral as sum f of n, and here we take the sum from k equals 0 to n minus 1. Okay, so let's see some examples of these computations. We'll start with f of n equals n. If f of n equals n, then delta f of n is f of n plus 1, which is just the identity n plus 1, minus f of n, which is just n. And that leaves us with 1, the constant function. As for sum of f applied to n, this is the sum from k equals 0 to n minus 1 of of k. And we actually just saw what this formula is. When you go up to n, it's n times n plus 1 over 2, so we shift that down 1, and we have n times n minus 1 over 2. Okay? So that's the computations for f of n equals n. Let's consider g of n equals 2 to the n. So if we take delta g of n, that's going to be 2 to the n plus 1 minus 2 to the n. If we factor out 2 to the n here, we get 2 minus 1, which is just 1. So we're left with 2 to the n. So delta g is actually equal to g. And if we take the sum g of n, we get the sum from k equals 0 to n minus 1 of 2 to the k. And we have formulas for geometric series. So we'll get 2 to the n minus 1 plus 1 is just 2 to the n minus 1 divided by 2 minus 1, which is just 1. So we're left with this. So g seems to be an interesting function where we take the discrete derivative and we get itself back, and we take the discrete integral and we get itself back shifted by a constant. So this seems to occupy a similar space to the exponential function e to the x in the discrete version of calculus. And something that you might have sensed based on those computations is that there is a fundamental theorem of discrete calculus, and that the discrete derivative and discrete integral are inverses of each other, much in the same way that the classical derivative and classical integral are. In particular, the theorem states if f of n is the, oh, I'm sorry, this should be f of lowercase n. F of n equals the discrete derivative of capital F of n, then the discrete integral of little f is capital F of n minus capital F of 0. Okay, and the proof is pretty straightforward, right? If we have the sum of f, okay, this is defined to be, or when we evaluate it at n at least, this is defined to be the sum from k equals 0 to n minus 1 of f of n. But from the first part of the theorem, or from the hypotheses, we know that this is equal to k equals 0 to n minus 1 of f of k plus 1. Sorry, this should be f of k. Minus capital F of k. And then we can just apply telescoping sums. Right? Every term you have, so starting with f of 0, you have f of 1 minus f of 0 plus f of 2 minus f of 1. F of 1s cancel. The next step, f of 2s cancel. And it keeps going up until you get to f of n minus f of 0 by telescoping. Okay, so it's pretty straightforward. I probably didn't even need to write it out. But it gives you an explicit formulation of this relationship between the discrete derivative and the discrete integral. And now we can consider what other properties of standard calculus translate to the discrete calculus. So we might hope that the power rule would apply. So let's consider, does the discrete derivative of x to the n equal nx to the n minus 1? And you can probably see pretty quickly that that's not the case. Let's consider delta x squared, or let's make it x squared. So this is x plus 1 squared minus x squared, which gives you 2x plus 1. Okay? So it's not, if it were the straightforward power rule, it would be 2x. But obviously this is not 2x, 2x plus 1. So we can see that the power rule is not obeyed. But if we change up our power function a little bit, it will be obeyed. So we're going to define the falling power, x to the underscore n, to be the product of the n integers where x is the largest. Okay, so if it's, for instance, x to the 3 underscore, it will be x times x minus 1 times x minus 2, because those are the 3 integers with x largest. Okay, so using this notation for the falling power, let's consider what happens when we have delta of x to the underscore n. We get x to the x plus 1 to the underscore n minus x to the underscore n. And this gives us x plus 1 times x minus 1, etc., down to x minus n plus 2. And from that, we're subtracting x times x minus 1, etc., down to x minus n plus 1. Okay, and here we can see that most of these factors are in common except for x plus 1 in the first term and x minus n plus 1 in the second term. So we have x all the way through x minus n plus 2, and that's just x to the n minus 1 underline times x plus 1 minus x minus n plus 1, and that is exactly n. So we get n times x to the n minus 1 underscore, and we get our power rule. Okay, so we just have to adjust which function we're looking at. We're not looking at pure powers, we're looking at falling powers. Now, shifting this a bit, we can also observe by the fundamental theorem of discrete calculus that the inverse power rule should also hold. So if we have the sum of x to the falling power n, this should give us 1 over n plus 1 times x to the falling power n plus 1. Okay. Now let's apply this power rule to get the formulas for the summations of squares and cubes in a different way than Ibn al-Haytham did it. So we'll start with summing k squared, and we'll take k equals 0 to n minus 1. Okay, well this is, you can check that k squared, you can express this in terms of falling powers as k to the underline 2 plus k to the underline 1. So when you take the summation, what you get is, applying the power rule, 1/3 k to the falling power 3 plus 1/2 k to the falling power 2. Okay. Or I suppose this should be n. Let's make this n. Since we summed over k. So that gives us, well, let's spell this out explicitly. So 1/3 n to the falling power 3. We'll put this over a common denominator. So we have 1/6 times 2 times n minus 1 times n minus 2 plus 3 times n minus 1. Okay, so we can factor out the n times n minus 1, and what we're left with is 2 times n minus 2, which is 2n minus 4, plus 3, or leaving you 2n minus 1. So we get n times n minus 1 times 2n minus 1 over 6, which is exactly the formula for a sum of squares. Now let's do this for cubes. Okay, k equals 0 to n minus 1 of k cubed is, well, we have to re-express k cubed as a sum of falling powers. And you can check that k underline 3 plus 3 times k underline 2 to the underline 2 plus k to the underline 1 is another way of writing k cubed. And summing, applying the power rule for discrete calculus, we get n to the underscore 4 over 4 plus 3 divided by 3 times n to the underscore 3 plus n to the underscore 2 divided by 2. Cool. So spelling this all out, we get, and I'll pull out a factor of a quarter. So we have n minus 1, n minus 2, n minus 3, plus n minus 1, n minus 2, and we need to have a factor of 4 there, plus 2 times n minus 1. Okay, so that's a lot of arithmetic, but once you do it all out, you get the formula n squared times n minus 1 squared all over 4. And that is the formula for a sum of cubes. I find this way of computing summations really satisfying, but if it's not your cup of tea, that's also fine. Some final thoughts on this section. First, mathematics flourished in the Islamic Golden Age. Ibn al-Haytham was an example of a great mathematician of that era, and he computed volumes for solids of revolution using Archimedes-style exhaustion arguments, okay, which in a modern interpretation look a lot like computation of volumes by way of disks. He also computed summations of kth powers. And discrete calculus, just as a tangent, is an intuitive way to derive these summation formulae in a way different from Ibn al-Haytham. Thank you so much for your attention.